Okay, now we'll discuss about database design. Okay, these are the chapter contents. First, we will discuss about bad database design or concept of anomalies. Generally, in databases, there are three kinds of anomalies are possible. One is your insertion anomaly, another one is your updation anomaly, and another one is your deletion anomaly. All those things anomalies present in a database or in a table. We will see all those things. Then we will see normalization. In next chapter is your normalization. Complete details about normalization we will study in next chapter, but only definition of normalization we will see in this chapter. Then functional dependency. This is the main aspect of your normalization. Functional dependency is the main aspect of normalization. We will see details about functional dependency in this chapter. There are types of functional dependency, trivial and non-trivial. Then Armstrong's inference axioms. In functional dependency, various rules are there. A total 7 number of rules are there. 3 are basic and 4 are derived rules. All those things are known as Armstrong's inference axioms. All those things we will see here. Then logical implication, then closure of set of attribute set, and these are the application of closure of attribute set. Okay, these are the 4 applications of closure of attribute set. All those things we will see here. Then closure of a functional dependency, then redundancy of FDs, then canonical cover and minimal cover. All those things we will see here. Okay. Now, already previous chapters I have already told you for a good database design, three levels of designs are involved. First one is your high level or conceptual design or a conceptual level design. Okay, and the second level is your representational or implementational level design. Representational or implementational level design. And third one is your low level or physical design. Okay, in this three level, a database generally design. Whenever an organization want to design a database for that organization, first what the organization will do, they generally calls a personnel from the software company. And that software personnel came to the organization and first they generally work on this high level or conceptual design. The high level or conceptual design deals with the requirement analysis phase. The software personnel who came from that software firm, they generally take the requirement of that organization, what the organization generally wants, and how the organization wants to implement, which part of the organization is they want to implement in database. That thing is analyzed by the software personnel. That is a requirement analysis phase. After taking the requirement from the organization, what other what software developer works, that is design of ER diagram. Okay, ER diagram design. Okay, after design of ER diagram, they generally create the relational model from the ER diagram. This ER diagram design and your relational model design is present in a representational or implementational level. But the requirement analysis phase is present in high level or conceptual level. In previous classes, I have already told you. Then in low level or physical design, how the tables, the relational model, whatever tables has to be created, how those will be implemented in physical level or in hard disk. Okay, all those things we will see here. Already we have discussed about relational requirement analysis phase. Already we have discussed about that. Already we know how to design a ER diagram from the requirement analysis. I have already explained this. And already we know how to design a relational model or tables from the ER diagram. But whatever tables we will create from the ER diagram, whether those tables are good design or not, how to know that? In this chapter, we will discuss that. Generally, several problems whenever from the ER diagram we will design a relational table, several problems are there. When we insert the data items into that table, we generally face several problems. Several anomalies are there. Generally, three kinds of anomalies may present in that table: insertion anomaly, deletion anomaly, and updation anomaly. Okay, and generally another problem is there. What redundancy problem is there? That means the repetition of data items may be present. And after creation of the table, then we have to analyze whether any kind of anomalies is present in that relation or any kind of redundancy problem is there. Okay, we have to remove or we have to reduce those problems. Understood? Then for that purpose, several mechanisms are there. All those things we will see. Now we will discuss about various anomalies related to your relational model. Suppose this is your student database. Okay, this is your student database. One table is there, and the fields are student roll number. This is your student roll number, student name, student section, faculty ID, faculty name, faculty salary. Okay, and the primary key is your student roll number here. This is your primary key. Okay, and these are the various data items present in the database. Suppose this is a what this is a part of the database which we have taken to make you understand the various anomalies and redundancy. Okay, redundancy means repetition of data items. In this case, just see here 101, then faculty name is your Alok and the salary is your 90,000. This record or this information is repeated in several records or several rows. Here 101 Alok 90,000, here 101 Alok 90,000, 101 Alok 90,000. This is your data redundancy. In a database, you cannot remove the redundancy completely, but you can reduce the redundancy. That's why whenever we are designing any relational model or whenever we are designing any database, at that moment we have to see whether redundancy is minimized or not. Okay, whether we can minimize the redundancy or not. Okay, that we have to see. Then now we'll see about anomalies. Generally, there are three kinds of anomalies. During insertion, if problem happens, then that is known as insertion anomaly. And during updation, if problem happens, that is known as updation anomaly. And during deletion, if problem happens, that is known as deletion anomaly. Okay. Then now each one we will see. Suppose one faculty joins the university, a new faculty joins the university. Can we add the faculty information without assigning any student to that faculty? Here, just try. Suppose the faculty ID is 107 and the name is here, suppose Omiya, and salary is suppose 87,000. Okay. Can we add this record without assigning any student to that faculty? Can we add this? If I will add this record, then already no student is assigned to this faculty. That's why I have to put null values here, here, and here. I have to put null values here because no student is assigned to that faculty. Okay, but can we assign null values in primary key attribute? Already we have discussed about relational model constant. One constant is there, entity integrity constant. Entity integrity constant tells you that null value cannot be inserted in primary key attribute or primary key attribute. You cannot insert null values. That's why we want to insert this information, but it violates the relational model constant. That's why we cannot insert this record or this information in this database. This is your insertion anomaly. That means we want to insert this information, but it violates the constraint of relational model. That's why we cannot able to insert this record. This is your insertion anomaly. Understood? Now we'll see deletion anomaly. Suppose the student with the roll number 605 1705605. The name of the student is here Pransu. Suppose the student left the college in between, then no need to keep his record in the student database. That's why we want to delete this record. Can we delete this record? If I will delete this record, no problem, it will delete it, but it will delete other information. The faculty ID 102, faculty name Sachin and salary 70,000. This information is not present in any other places. That's why whenever I want to delete this part of the information, I will lose some information. Okay, that's why I want to delete this information. What student roll number 17056 and Pransu CS10. But if I will delete this record, this is information, then I will lose some information from the database. That's why I cannot delete this record. I cannot delete this record. This is your deletion anomaly. This is your insertion anomaly. This is your deletion anomaly. Okay. Suppose the faculty ID with 101, his salary has increased from suppose 90,000 to 1 lakh. Suppose 90,000 to 1 lakh. then I have updated the salary of what faculty ID 101. If I will update the salary of the faculty ID 101 in this one place, in other places it is 90,000 is there. That means it will conflict. The result will conflict. This is your updation anomaly. That means if I want to update the salary of faculty ID 101, then I have to update the salary in every field. That means here 5 fields are there. Here also I have to change it. Here also I have to change it. Here also I have to change it. This is your updation anomaly. That means it is creating, if I will update the salary in one place, then it will create conflict results. That means in some field, the salary of faculty ID 101 is showing 1 lakh, and in some field, the salary of the 101 is showing 90,000. Okay, this is your updation anomaly. And whenever you will design any database, suppose from ER diagram you have designed one table, then that should be free from all kinds of anomalies. That means in that table you have to check whether insertion anomaly is there, whether deletion anomaly is there, or whether updation anomaly is there. No such anomalies should be present in a database or in a table. And redundancy, if you we have to check whether we can reduce the redundancy or not, because redundancy cannot be removed completely, but anomalies has to be removed completely, but redundancy cannot be removed completely. We have to design the database in such a way that the redundancy will be minimized. Okay, then these are the problems, these are the anomalies, and the redundancy problem is there. All those things we have understood here. Now we'll see, all those things are explained. I have already explained this thing. Okay, now how to remove all kinds of anomalies and remove the redundancy. How to remove the redundancy and how to reduce the redundancy and how to remove the anomalies. For that purpose, one concept is there. The name of that concept is your normalization. Then what is normalization? In next chapter, we will see complete full details about normalization. But in this chapter, only definition we will see. Normalization is the process of decomposition of a relation or table to reduce the redundancy and to remove the anomalies. Okay, that means the process of decomposing. That means suppose here student table is there, here anomalies are present, and here redundancy is present. Okay, and if we will apply normalization what procedure here, then we can reduce or we can decompose this relation into multiple relation, so that all the anomalies will be removed and we can reduce the redundancy. And what is normalization? Normalization is the process of decomposition of a relation to reduce the redundancy and to remove the anomalies. That thing we will see here. Okay. The student table is, suppose I will divide the student table into two tables, student database into two parts. In one table, I will keep student roll number, student name, student section, and faculty ID. And here, student roll number is the primary. Okay, this is your student table. And another table is your faculty table. In this, faculty ID is the primary key. Okay, and faculty name and faculty salary is there. Okay, then I will keep all the records, whatever records are present in that student database, all the records I will put, all those records I will put in two tables. Okay, here. Now we have to see whether redundancy is present or not. In the student database, here 101 alloc 90,000, that was present 5 times. 1, 2, 3, 4, 5. 1, 2, 3, 4, 4 times. Okay, but in this case, only one time 101 alloc 90,000 is present. But here some redundancy is there, 101, 101, 101, 101. Okay, but the redundancy has been removed, reduced. Okay, it has not been removed, but it has reduced. Okay. Now we'll see whether anomalies are present or not. First, suppose a new faculty with faculty ID 107 joins the university. Then can we insert his record before assigning a student to that faculty? We will try here. Suppose 107 is the faculty ID. Name is your Omeo. And salary is your, suppose 87,000. Yes, we can put it without assigning any student to that faculty. Okay, because your faculty ID is the primary key. Primary key does not contain null values here. Some information is there. That means we can insert. That means insertion anomaly is not present here. Now we'll see. Suppose in between the semester, suppose one student, Pransu, suppose left the university. Can we delete his information? We want to delete his information. Can we delete his information? If we delete the information, does it miss any other information? We will see. Suppose I will delete this information. Does it delete 102 faculty information? No. 102 faculty information is present in faculty table. That means 102 Sachin 70,000. That means we can delete this information from here. That means the deletion anomaly is not present here. Now we'll see updates on anomaly. Suppose the salary of faculty ID 101, that is your faculty name is your Alok, his salary is increased from 90,000 to suppose 1 lakh rupees. Can we increase? Suppose 90,000 to 1 lakh rupees. We will update it in one place. Can we update that? Yes, we can update that. Only one place we have to update. No data inconsistency arises in this case. Okay, that means updation anomaly is not present here. That means previously student database was there, and we have what decomposed that student database into two tables. One is your student table, another one is a faculty table. By decomposing that original table into multiple tables, we have removed all the anomalies. No anomalies is present, and we have reduced the redundancy. Okay, and this process is known as normalization. Okay, you will see normalization details in next chapter. Okay, and this is all about your normalization. Now we'll see functional dependency. Functional dependency is the building block of normalization principle. Mm, okay, functional dependency is the building block of normalization principle. Then attribute A in a relation schema R functionally determines another attribute B in relation R if for a given value A1 of A there is a single specific value B1 of B in relation R of R. Okay, what is this? I will explain this in details in this table. Okay, suppose generally the functional dependency is represented by one attribute is functional, whether functionally determines for another attribute of the relation. Suppose this is your relation R, and in this relation, can we say A determines B? A functionally determines B. We can say A functionally determining B when for each value of in A, there exists a unique value in B. For each value in A, there exists a unique value in B. That means, suppose in this case, we will see, suppose A1 is there, that means A1 is associated with B1. That means whenever A1 repeats here, this value should repeat. Okay, that means for each value of A1 here in A, there is a particular value B1 in B. Then we can say A functionally determining B. Can we say A functionally determining B in this case here? For A1, A1 value is B1. Again, when A1 repeats, B1 is same value is there, same value is repeating. That means exist. Then is A1 repeats here? No. That means for A1 it is satisfying. Then for A2, for all tuples we have to see. For A2, one value is your B2. Then again we have to see whether A2 is present. Yes, A2 is present, but one value is B3 here. That means if B2 repeats here, then we can say functional dependency or functional dependency is maintained here. But in this case, for single value A2, there exist multiple value in B. That means one is your B2, another one is your B3. That's why A determining B is not possible in this case. We cannot say A functionally determining B here. Understood? Can we say A functionally determining C in this case? For each value of A, there exists a single value in C. Okay, for A1, C1 is there. When A1 repeats here, okay, C3 is there. That means we cannot say A determining C, because for A1, two values are there. One is your C1, another value is your C3. That means A determining C, we cannot say. A is functionally determining C, we cannot say like that. Okay. Then can we say B determining C here? Just check for each value of B whether a unique value in C is present or not. For B1, one value is there, C1. Again B1 repeats here, but another value is your C3. That means for B1, two values are there. Your C1 is there, your C3 is there. That means B determining C is also not possible. That means B is not functionally determining C. Then check for A determining C. Suppose I will modify this table. Suppose I will change this C3 value from C3 to suppose C1. Okay, C1. Then I will check for A determining C. Whether A determining A functionally determines C or not, just check here. For each value of A, if there exists unique value in C, then we can say A determines C. Okay, for A1, C1 is present here. Then when A1 repeats in this case, another C1 is present here, same value is repeating here, no problem. Then for A2, C2 is present. Again A2 repeats here, then A2, C2 is present, no problem. Then for A3, C4 is present. That means A determining C is here functionally determination. That means A functionally determining C. We can say like that. Then check for B determining C, whether B is functionally determining C or not. For here, for B1, C1 is there, B1 is associated with C1. Again, B1 repeats here. For B1, C1 is present. Okay, no problem. Then for B2, C2 is present. Then again, B2 repeats. No. Then again, just check for B3, C2 is present. Okay, B3 is also unique value. Then for B4, C4 is present. That means B determining C, B functionally determining C. This is correct. Okay. Now check for AB determining C. AB determining C. For AB means A1, B1 determining C1. Okay. Is A1, B1 repeats here? Yes, A1, B1 repeats here, but it is determining C1. Okay, no problem. Then A2, B2 determining C2. Is A2, B2 repeat? No. Okay. Then A2, B3 determining C2. Okay, unique value. Then A3, B3 determining C4. That means AB determining C is a functional dependency in this case. Then we will see whether BC determining A is a functional dependency or not. Okay, BC determining A. BC means this one determining A. B1 C1 determining A1. Okay, is B1 C1 repeats here? Yes, B1 C1 repeats here, but it determining A1, same A1. Okay, no problem. Then B2 C2 is determining A2. Is B2 C2 repeats here? No, B2 C2 is not repeating. Then B3 C2 determining A2. Okay, then B4 C4 determining A3. Okay, that means BC determining A is also a functional dependency. Similarly, now we will see A determining A. A determining A. Is it a functional dependency? A means A1 is determining A1, A2 is determining A2, A1 is determining A1, A2 is determining A2, and A3 is determining A3. That means this is always true. Such kind of functional dependency are always true. Okay, the same attribute determining the same attribute. This is always true. And another is suppose AB determining A. Just see. This is also always true. Okay, we will check this. Suppose A1 B1 determining A1. Again, A1 B1 repeats here. A1 B1 determining A1. A2 B2 determining A2. Then A2 B3 determining A2. Then A3 B4 determining A3. These are always true. Okay. Then B determining B, just check. This is also always true. And such kind of functional dependency are named as trivial functional dependency. And such kind of functional dependencies are known as non-trivial functional dependency. What is trivial functional dependency? We can say A determining B is a trivial functional dependency if B is a subset or equal to A. In this case, just see. This part RHS is equal to LHS. Okay, that may be the case, or this may be the RHS subset LHS. Okay, RHS is a subset of LHS. Okay, if from these two conditions any condition is satisfied, that means we can say that this functional dependency is a trivial functional dependency. What is a non-trivial functional dependency? A determining B is a non-trivial functional dependency if A intersection B is equal to 5. That means there should not be any common attribute in between LHS and RHS. In this case, A determining C, A and C are different. B determining C, B and C are different. AB determining C, AB and C are different. BC determining A, BC and A are different. In this case, we can say this is a non-trivial functional dependency. That means functional dependency can be of two types. One is your trivial functional dependency, another one is your non-trivial functional dependency. Then what is a functional dependency? One attribute of a relation is functionally determining another attribute of the same relation if for each value of first LHS there exists a unique value in RHS. Then we can say that A determining B, A functional determining B. Then other points are the symbolic expression of the functional dependency is A determining B. Functional dependency is represented like this arrow symbol. Okay, where A LHS of functional dependency is known as determinant and B RHS of functional dependency is known as dependent. Okay. In other words, if a function A functionally determines B in R, then it is invalid to have two or more tuples that have the same A value but different B values in R. Already we have discussed this. That means suppose A1 is there and A1 has RHS, but suppose we will check for A determining B. A1 has one value B1 and A1 has one value B2 here. Then we cannot say that A determining B. That means whenever A1 is associated with B1 in one part, that should be every time. Whenever A1 will be repeated in this part, the B1 value should be repeated. Then only we can say A determining B. Okay. From student schema, we can infer the student roll number to student name because all tuples of student with a given roll number value also have the same name value. Okay, this can be a functional dependency. Okay, then FD, functional dependency is a constraint between two sets of attributes in a relation from a database. Okay, this is all about your functional dependency, and this is your two types of functional dependencies are there. One is your trivial functional dependency and another one is your non-trivial functional dependency. What is a trivial functional dependency? A functional dependency X determining Y is a trivial functional dependency if Y is a subset of X, or we can say Y is a subset or equal to X. This is your trivial functional dependency. In non-trivial functional dependency, X determining Y is present. It is known as non-trivial functional dependency if Y intersection X is equal to 5. That means the LHS and the RHS, but there should not be any common attributes in between. Okay, this is all about your trivial and non-trivial. Then now we'll discuss Armstrong's inference axioms. The inference axioms of rules allow user to infer the FDs that are satisfied by a relation. Okay. Let R, X, Y, Z, W, where X, Y, Z, W are arbitrary subsets of the set of attributes of a universal relation schema R. In Armstrong inference axiom, there are three fundamental inference rules and four derived inference rules. First, we will see about three fundamental inference rules. First one is a reflexivity rule. What reflexivity rule tells you? If Y is a subset of X, then X determining Y. That means this is the opposite of trivial functional dependency. In trivial functional dependency, what we have said? Suppose X determining Y. Here X determining Y is known as trivial if Y is a subset equal to X. Okay. If I will say Y is a subset of X, then X determining Y. This is your reflexivity rule. Okay. Similarly, augmentation rule. If X determining Y, then XZ determining YZ. That means if X is determining Y, if any attribute, same attribute added in LHS part and RHS part, that will also functionally determination. That means XZ will functionally determine YZ. This is your augmentation rule because we have augmented another attribute in both sides, LHS and RHS. Then another one is your transitivity rule. What is transitivity rule? Normal transitive rule. If X is determining Y and Y is determining Z, then we can say X functionally determines Z. Okay, this is normal transitive rule. These three are known as fundamental inference rule. First one, reflexivity rule is the opposite of trivial functional dependency. Augmentation rule, if we add a attribute, same attribute to the LHS part and RHS part of a functional dependency, then that will be also a functional dependency. And transitivity rule says that if X is determining Y and Y is determining Z, then X will determine Z. These are the three fundamental inference rules. Now we'll see for secondary inference rules. Okay. First one is your union or additive rule. What union or additive rule says? If x is determining y and x is determining z, then we can say x is determining yz. If the LHS part is your same and RHS part is different in two what functional dependencies, then we can combine the RHS part. X functionally determines yz. We can say like that. This is your union or additive rule. Okay. Then decomposition rule. What is decomposition rule? If x is determining yz, then we can say x is determining y and x is determining z. That means decomposition rule is the opposite of union or additive rule. Here we are adding, that means x determining y and y determining z, that is x determining yz. But in this case, x determining yz, this part is given, then we can divide it into x determining y and x determining z. Okay, this is the opposite. These two are opposite to each other. Okay, then composition rule. What is composition rule? If x is determining y and z is determining w, then we can say we can add left hand side part xz determining yz, and we can add right hand side part, and they will be functional determination. That means we can say xz determining yz. Okay, this is your composition rule. Similarly, pseudo transitivity rule. What is pseudo transitivity rule? If x is determining y and y does w is determining z, this is very important. Okay, x is determining y and yw determining z, then we can say xw determining z. That means in this case, in this, in left hand side part, we can here right hand side y is present, then that can be replaced by your x. That's why xw determining z. This is very important. We will use this in most of the cases for determining what candidate key in future. Okay, this rule is very important. Okay, which are the all 4 secondary inference rules? We will see logical implication. Okay, suppose one relation schema R is present and a set of functional dependency F is present. Let FD functional dependency X determining Y is not in F functional dependency set. Then F can be said to logically imply X determining Y if for every relation R on the relation schema R that satisfies the FD in F, the relation R also satisfies X determining Y. And the logical implication is determining by this F such that equal to X determining Y. Okay, it tells that, suppose let's take one example. Suppose R A B C D, a relation is there where A B C D are 4 attributes, and the functional determination set is A determining B, B determining C, B C determining D. Then check for A determining B whether we can say this functional dependency set logically imply A determining D or not. Then how to check that A determining D is logically implied from this or not? For checking of that, from this, can we infer from this functional dependency set, can we infer this A determining D or not? Just check that. In this case, just see BC determining D is present, and I can replace C by A, because in pseudo transitive rule we have seen if in the right hand side some attribute present and in left hand side we can replace that attribute with the left hand side of that attribute. That means C can be replaced by A. When I will replace C by A, I can say BA determining D. Again, here I can replace B here, B with A, then B can be replaced by A. That means AA determining D. A is nothing but A determining D. That means from this functional dependency set, we can infer, logically infer this functional dependency. Then we can say that this functional dependency set F logically infer A functionally determining D. And another one is your given F functional dependency set is A determining B and C determining D with C subset equal to B, so that F logically determines A determining D in this case. Okay, suppose C is determining D and it is given that C is subset equal to B. That means we can replace C by B. Then we can say B determining D. In this case, B can be replaced by A. B can be replaced by A. Then I can say A determining D. Okay, that means if functional dependency set is there and this condition is given, then from that this functional we can say that functional dependency F logically infer a functionality determining D. Okay, this is a logical implication. That means suppose one relation R is given and one functional dependency set is given, and in that functional dependency set one functional dependency is not present, suppose A determining D, then can we say from this functional dependency set this functional dependency can be logically inferred or not? How to check that? If from this functional dependency, using this functional dependency, using Armstrong axioms, if we can infer this functional dependency, then we can say that this functional dependency set can logically infer this functional dependency. Understood? This is a logical implication. Now we'll see closure of a set of attribute. How to find out the closure of a set of attribute, or what do you mean by closure of a set of attribute? Okay, a given set of attribute X and a set of functional dependency F, then the closure of set of attribute X under F denotes as X closure. That means X closure. This is represented like this. Okay, and is the set of attributes A that can derive from X by applying the Armstrong inference axiom to the functional dependency of F. Okay, now we will take one example. Suppose R, A, B, C, D, these are the attributes of a relation R, and this is the functional dependency set. Then how to find out A closure? A closure, how to find out that A can functionally determine A? Okay, and using Armstrong axiom, A can functionally determine C. Okay, I can write C here. Okay, and from AC, can we infer any other attributes of this relation? No. That means A closure is equal to AC. Similarly, we can find out B closure. B closure is equal to B can logically infer B. Similarly, in this case, B functionally determining D. That's why we can write here D. That means B can logically infer D. Then X from this BD, can we logically infer any other attributes using Armstrong axiom? No. That means P closure is equal to PD. Then we can find out C closure. C closure will be how much? C closure will be C, because one attribute logically infer itself. Okay, that is your C. Then from C, any other attribute can be derived? No. Then we will find out D closure. D closure, D can logically infer D. Okay. Any other attribute can be logically derived? No. That means D closure is equal to D. Now we will find out AB closure. AB closure means AB first logically infer AB. Then from A we can infer C. We can write here C. And from B we can infer D. We can write here. All the attributes have came. That means AB closure. AB can functionally determine all the attributes of this relation. Similarly, we can find out AC closure. AC closure means it will first logically infer AC. Then from AC, can we infer any other attributes? No. No other attributes can be logically inferred using Armstrong axioms. Okay, that means AC closure is equal to AC. Now we'll find out AD closure. AD closure means first AD will come here. From A we can infer C. Okay, then C will come. Then from D, can we infer anything? No. That means ADC. That means AD closure will be ADC. Then similarly, we can find out BC closure. First, we have to write BC here because BC can be logically infer BC from BC. Then from B, we can infer D. Then we can write D here. Okay. Then BCD. Then BC closure will be here BCD. Okay. Then now we will find out BD closure. First, we have to write BD. B, D, then from here any other attribute can be inferred? No. Then CD closure, first we have to write CD, C and D. Any other attribute can be inferred? No. Then ABC closure, first ABC will come, and from B we can derive D, that means D, that means all attributes are derived. That means ABC closure is equal to ABCD. Similarly, ABD closure, that means first we have to write ABD and ABD, then from A we can infer C, that means C will come, that means all attributes came here. Then similarly BCD closure, first BCD will come. Okay, then from B we can infer D, or D is already present, that means can we take A here? No. Okay, that means BCD closure will be your BCD. Then ABCD closure means ABCD. All attributes will come. Okay, in this way we can find out the closure of any attribute or attribute set. Okay, that means first you take that attribute. When you find out the closure of that attribute, using Armstrong axioms, so whatever attributes can be inferred from this attribute, that we have to write here. Okay, this is your closure of a attribute set. Similarly, suppose another relation R is given and functional dependency set is given, then we can find out X closure here, we can find out Y closure, we can find out Z closure. Similarly, we can find out XY closure, we can find out YZ closure, XZ closure, XYZ closure. Similarly, we can find out all how much will be X closure. X closure, X logically in for X, then from X Y can be derived Y, then from Y Z can be derived Z. That means all the attributes can be derived. Y closure, Y can be derived from Y, Z can be derived, then YZ. Then Z closure, Z can be derived from Z. Any other attribute? No. XY closure, then XY will come here, X Y, and from Y Z can be derived, then Z. Okay, then YZ closure. Okay, YZ can be derived. X can be derived here? No. XZ closure, X Z, from X Y can be derived. XYZ closure, XYZ. Okay, in this way you can find out closure of any attribute or attribute set. Okay, this is all about closure of set of attributes. Now we will see uses of closure of set of attributes. Okay, first one is your testing for key. To test whether a X is key or not, X closure is computed, and X is a key if X closure contains all the attributes of R. X is a candidate key if none of the its subset is a key. Okay, we will see how to find out the key. Suppose R is a relation. Okay, suppose R is a relation and A, B, C, D are four attributes. Then A, how to find out the key of this relation R? Suppose A determining B, these are the functional dependency set is there. B determining C is there, C determining D is there. Then we have to find out A closure. If A closure functionally determines all the attributes of the relation, that means A, B, C, D. If A closure is A, B, C, D, then we can say A is a key. Okay, then how to find out the candidate key? If this is the minimal one, that means suppose A closure is determining ABCD and AB closure is determining ABCD. ABC closure is determining ABCD. Then which one is your candidate key? A will be your candidate key because it functionally determines all the attributes of the relation as well as it is minimal one. Then it will be your candidate key. Okay, we will see it later on. Lot many examples we will do. Then testing functional dependency. Suppose to check whether a functional dependency X determining Y holds or not. Okay, how to find out that? Suppose R ABCD is given and some functional dependency set A determining B, B determining C, C determining D is there. Then how to check whether A determining D is a functional dependency or not? Then first you have to check whether D is a subset of X closure or not. Then without taking first you take A, then find out A closure here. A closure will be here A B C D, and D is present here. The right hand side which is derived by A, that is present here. That means this is a valid functional dependency. Okay, in this way we can check. Now we'll see these are the four applications of closure of attribute set. First one is your finding all candidate key. Okay, finding all candidate key, we will see that. Then checking whether an attribute set is a super key or candidate key, we will see that. Then computing F closure. Okay, then membership test. Then first we will see how to find out the candidate keys. Before that we will know about keys. Okay, there are generally various kind of keys are there. Already I have explained you all the keys in previous classes, but again I am explaining. First one is here, there are various kind of keys are there. Super keys there, keys there, candidate keys there, primary keys there, alternate keys there, foreign keys there. Then what is a super key? How to find out the super key? An attribute or set of attribute that has uniqueness property is called super key. And if an attribute set closure contains all the attributes of a relation, then it is called a super key. That means suppose R is a relation and A, B, C, D are 4 attributes and some functional dependency set is given, and if we will find out A closure and it is deriving all the attributes of this relation using this functional dependency set, then we can say A is a super key. Okay, suppose when A is a super key, AB will also a super key. When ABC will also a super key. Okay, that means the closure of any attribute or set of attribute which derives all the attribute of the relation is known as super key. Okay, then what is a key? An attribute or set of attribute that has uniqueness and minimality property is called a key. Okay, in this case, suppose A closure is deriving all the attributes. In this example, A closure is deriving all the attributes, AB closure is deriving all the attributes, ABCD closure is deriving all the attributes. Then which will be a key? A will be a key because this is uniqueness property satisfied by A, AB, ABC. But minimality property is satisfied by A. That means only single attribute, minimum number of attribute whose closure derives all the attributes of the functional relation is satisfy minimum minimality property. Okay, then this is your key. Suppose one relation R is there and functional dependency set is there, and here suppose A closure is deriving ABCD, that means all the attributes. Similarly, B closure is deriving all the attributes ABCD. C closure is deriving suppose all the attributes ABCD, and AB closure is deriving all the attributes suppose ABCD. ABC closure is deriving all the attributes ABCD. Then which one is a key? Here A, B, C are key because these are satisfying the minimality property as well as uniqueness property. Then which are super key? A is a super key, B is a super key, C is a super key, AB is a super key, ABC is a super key. We can say any attribute added to a key becomes a super key. Suppose A is a key. If I will add B to it, then it will be a super key. Then A, B, B, C I will add, ABC will be a super key. Suppose A, B, C, D I will add, it will also a super key. That means we can say in key, any attribute is added, that becomes a super key. Okay, in other way, we can say like that. Then what is candidate key? The set of all the keys. Okay, in this case, what are the various keys? A is a key, B is a key, C is a key. The set of all the keys are candidate key. That means the candidate key set is here A, B, C. In this case. Then what is a primary key? One of the candidate key that is selected by the database designer for a particular application is known as primary key. That means any of the key from the candidate key set can be selected as a primary key. Then what is alternate key? All the candidate keys except primary key are called the alternate key. In this case, the candidate key set contains 3 keys A, B, C. And A, suppose A is selected by the database designer for a particular application for become the key or primary key. Then BC is known as the alternate key. Okay, then what is foreign key? An attribute or set of attribute of one relation that refers to the primary key of same or other relation is called foreign key. Already I have explained foreign key in previous classes. Okay, foreign key means suppose generally to join two relations or to set up relationship among two relations, generally what foreign key is used. In this case, in this place I am explaining. Okay, in this place I am explaining. Suppose one relation R1 is there, another relation R2 is there, okay, and A, B, C are 3 attributes of R1 and X, Y, Z are 3 attributes of R2. Okay, then it is an attribute or set of attribute which refers to the primary key of another table. Suppose R1, the primary key of R1 is A, the primary key of R2 is your X. Suppose X specifies or X refers to A, then X is known as the foreign key for this relation for R1. Okay, and the foreign key attribute can refer to primary key of the same attribute, a same table, as well as primary key of another table. Suppose in R2 we can take Z as a foreign key, which can refer to the X, okay, which is the primary key. Okay, that means foreign key is an attribute or a set of attribute which refers to the primary key of the same relation or another relations. is known as foreign key. Okay, these are the different kind of keys, but basically we will consider here how to find out the candidate key as a super keys in this case. Okay, and finding all candidate keys in this case. Suppose first example, R is a relation with A, B, C. Three attributes are there. Then the functional dependency set is A determining B and B determining C. Then what are the various candidate keys possible in this case here? First, we have to find out the A closure. From starting from minimum one, we have to start. A closure will be how much? A, B, C. Okay. Then we can find out B closure, B, C. Okay. We can find out C closure here, then C. Okay. Then A closure is functionally determining all the attributes A, B, C. That means A can be a super key. Okay, and as it is the minimal one, that means A will be a key or candidate key. Okay, B is not determining all the attributes, that means we cannot say B as a key or a super key. C cannot be a super key. Okay, and the minimal one is your A, and anything we will take, suppose AB closure I will take, that will not minimal one. That's why here the only candidate key possible is your candidate key is equal to A in this case. In case of second one, RABC, the functional dependency says A determining B, B determining C, C determining A. In this case, we have to find out A closure first. A closure is equal to ABC. From A we can derive A, from A we can derive B, from B we can derive C, ABC. Okay, all the attributes derived. Then B closure we have to find out. B closure will be B, C, A. Similarly, C closure will be C, A, B. Okay, that means A, B, C, three all are your candidate key in this case, because candidate key all are your super key A, B, C, and any attribute added to it. That means if I will find out a B closure, then also it will derive all the attributes, but this will not minimal one. That's why the minimal one we have to consider. That's why A, B, C we can take. In shortcut manner, we can find out like this. Suppose we will find out A closure, and A closure is deriving ABC, suppose, then no need to check individual one. First you see A in the right hand side of this functional dependency. That means A is present here. That means A can be replaced by C. C. That means C closure will also derive all the attributes. Again, just check C at the right hand side of the functional dependency. Okay, B is deriving C. C is present here. That means we can replace C with B. Okay, B closure. Okay, that means A, B, C are three candidate keys here. Okay, in this case we will find out. Again we will find out A closure. A closure will be how much? A, C. Okay, then here B closure. B closure will be here B, D. Then we have to take combination of all to A, B closure. Then A, B closure will be A, B, C, D. Okay, it is deriving all the attributes. Then we have to see whether A and B are present at the right hand side or not. It is not present at right hand side, that means we cannot replace these attributes by any other attributes. Okay, then can BC closure derive all the attributes? B, C, D, no, that means it cannot be a key. Then similarly D closure cannot be a key. That means here only candidate key possible is here AB. Okay, similarly in this case we will find out. In this case, R, A, B, C, D. A, B, C, D, four attributes are there. The functional dependency set is A, B to C, C to D, A to B. Okay. Then first take A, B closure. Then A, B closure can derive A, B, C, D. Okay, four attributes. Then just see whether A, B is present at the right hand side of the functional dependency. Yes, B is present. That means B can be replaced by A. That means we can replace B with A. That means it will be AA. A is nothing but A closure. That means A closure can derive ABCD. Then just check whether A is present at the right hand side or not. No, A is not present. That means here only candidate key possible is equal to A. Understood? And in this case, we have to find out R, A, B, C, D, the functional dependency A, B to C, B to D, D to B. Okay, now you take AB closure. Now AB closure will be A, B, C, D. Okay. Now just check whether any attribute is present at right hand side. Yes, B is present. That means B can be replaced by D. That means AD closure will also functionally determine all the attributes A, B, C, D. Okay. Now just check whether A and D is present at right hand side. Yes, D can be replaced by B, but already B is there here, AB closure. Okay. Then just check any other attribute A. No. That means here the candidate keys possible are AB and AD. Okay, D can be replaced by B. Okay, and then can I take C? AB, AD. C is not present in AB, B and A. Okay, these are the two candidate keys possible in this case. Okay, now we'll see checking whether an attribute set is a candidate key or not. Okay, how to find out that? Suppose check for AB. In this case, suppose R, A, B, C, D, E, this is a relation and these are the functional dependency set. And here it is asked that whether AB is a candidate key in this case or not. First, we have to find out all the candidate key. Before that, first you find out AB closure. Directly you can check AB closure will be how much using this functional dependency. A, B, then from AB we can derive C, from C we can derive D, from D we can derive E. Okay, B, C, D, E. Then you just check whether A and B are present at left hand side, right hand side of the functional dependency or not. Yes, B is present at right hand side. That means B can be replaced by A. That means this will be AA. That means A closure can derive all the attributes. That means AB is not minimal one. This can be a super key, but A is the minimal one. Okay. Then what are the other candidate keys possible here? Is A is present at right hand side? No. That means the only candidate key is possible in this case is here A. And AB cannot be a candidate key in this case. Okay. Check for AD in this case. Okay. Suppose R, A, B, C, D, E is a relation and this is the functional dependency set. These are all. Then how to check AD? AD closure we have to find out. AD closure is equal to AD B. From A we can infer B. From B we can infer CD. So or D already present. From D we can infer E. That means A, B, C, D, E. All the attributes are derived. That means it can be a super key. Whether it can be candidate key or not, we have to check. Okay. Whether A or D, any attribute is present at right hand side or not, we have to check. Yes, D is present. That means D can be replaced by AB. That means now it will be AAB is nothing but AB. Now AB closure is determining ABCDE. Okay, that means AB can be a super key. Okay. Now whether any attributes is present which can be present at right hand side. Yes, B is present at right hand side. That means B can be replaced by A. I can replace B with A. That means it will be A. That means A closure can infer all the attributes. That means this is your unique. This satisfies minimality property as well as uniqueness property. That means the candidate key here is your A. That means this cannot be a candidate key in this case. Okay. In this way, you can check whether a particular key is your candidate key or not. In this way, you can check. Okay. Now we'll discuss closure of a set of functional dependency. Okay. What is closure of a set of functional dependency? Given a set of functional dependency F for a relation schema R, we define F closure. This is represented as F closure or closure of F to be the set of all functional dependencies that are logically implied by F. Mathematically, F is equal to X functionally determining Y such that F logically infer X determining Y. Okay. Then suppose one relation R is given with some attribute, suppose A, B, C, D, and some functional dependency set is there, suppose A determining B and B determining C. Then how to find out the F closure? That means the functional dependency of all the functional dependency of this functional dependency set. How to find out that? To find out that, these are the procedure to generate the all FDs that can be derived from F. The steps are: apply the inference axioms to all single attributes and use the FDs of F whenever it is applicable. Then second, apply the inference axioms to all combination of two attributes and use the functional dependencies of F whenever it is applicable. First, single attribute, here, then two attribute. Next, apply the inference axiom to all combinations of the three attributes and use the FDs of F when necessary. Then proceed in this manner for as many different attributes as are in F. Now, take one example and do this. Okay, suppose here we want to find out the closure of this F closure. I want to find out here R is a relation and A, B, C are three attributes and the functional dependency set is here A determining B and B determining C. Then how to find out F closure? To find out F closure in this case, first phi closure is equal to phi. This is one functional dependency here. Then now single attribute will take A closure is equal to how much? A, B, C. Three attributes are there. A is functionally determining three attributes. That means total 8 number of functional dependencies are possible. Here 1 number of functional dependencies is possible. Here 8 number of functional dependencies is possible. How 8 number of functional dependencies is possible? This I am explaining. Suppose A can determine phi, A can determine A can determine B, A can determine C, A can determine AB, A can determine BC, A can determine AC, and A can determine ABC. How many number of functional dependencies there? 1, 2, 3, 4, 5, 6, 7, 8. That's why I have written 8. That means when you take closure of one attribute and you will take some attributes here, if 3 number of attributes are there, then 2 to the power 3 is equal to 8 number of functional dependency can be possible. Okay, then we will take single attribute B. Here B closure will be your BC. Two attributes here means 2 to the power 2 is equal to 4 functional dependency can be possible. Then your C closure will be your C, single attribute, that means 2 to the power 1 is equal to 2. One functional dependency is a C functional determining phi, another one is a C functional determining C. Okay, now we'll take two attributes. Suppose AB closure will be ABC, again three attributes, that means 8 number of functional dependencies are possible. Similarly, BC closure will be how much? BC only, then 2, that means 2 to the power 2 is equal to 4 functional dependencies are possible. Then your AC closure will be your ABC 3, that means 8 functional dependencies are possible. Then you will take combination of 2 we have completed, the combination of 3 ABC closure will be your ABC, that means 8. Total how many number of functional dependencies are possible here? Total 43 number of functional dependencies are possible in this case. Okay, then what are the all functional dependency? Phi determining phi is a functional dependency, and A closure is equal to ABC, that means these are the various functional dependency. In this case B closure is equal to BC, that means similarly we can find out four functional dependency: B determining phi, B determining B, B determining C, then B determining BC. These are the four functional dependency in this case. In this case two functional dependencies are the C determining phi is 1, then C determining C is 1, then AB determining ABC. Then there are 8 number of possibilities are there functional dependency. In this way you can find out all the functional dependencies. Okay, okay, this is your for question number 1 we have completed. Now we will compute for question number 2. Okay, now I am erasing this. Okay, pointer option, then eraser. Sorry. Okay, in this case we will find out for second one. Okay, uh, okay, here first one is your phi closure is equal to phi. This is your first functional dependency. Then your A closure will find out single attribute. A closure is equal to AB. That means 2. That means 2 to the power 2 is equal to 4. Functional dependencies are possible. Then B closure will be your BA 2. That means 4 functional dependencies are possible. Then AB combination of 2. AB closure is equal to AB. 2 to the power 2 is equal to 4. Total how many number of possible? 12, 1, 13. 13 number of functional dependencies are possible in this case. Okay, then we will find out the functional dependencies for this case. Okay, okay, in this case, again, high closure will be your high. This is your first one functional dependency. Then single attributes will take a closure is equal to a. This is your 1, 2 to the power 1 is equal to 2 functional dependencies. Then your b closure will be your only b and a. b a b determining c, that means 3c. Okay, abc, that means 3 to the power 3 is equal to 8. Then your c closure will be equal to cb a again, that means 3, that means 8. Then your AB closure combination of 2, AB closure will be your ABC, that means 8. Then your ABBC closure, BC closure will be your ABC, then 8 again. Then AC closure will be your APC, then again 8. Then ABC closure will be your ABC, then again 8. Okay, then total number of functional dependencies in this case are 8 to 1, that means total number is here 51. Okay, this is your F closure. But in this case, how 8 number of functional dependencies are possible? In this way, you have to evaluate. Suppose A closure is equal to ABC. These are the various functional dependencies for this what functional dependency. So similarly, you can find out total 51 number of functional dependencies in this case. Okay, this is all about F closure. Closure of a set of functional dependency. Okay. Here, one example is there. Your RABC is there. Functional dependencies A to B and A to C. Then how many number of functional dependencies are possible in this case? First one is your 5 to 5 is possible. One functional dependency. Then A closure we have to find out. A closure is equal to AB, then C. That means 8. Then your B closure. B closure will be your only B. That means 2 to the power 1 is equal to 2. Then C closure is equal to C, that means 2. Then AB closure will be your ABC, that means 2 to the power 3 is equal to 8. Then BC closure will be your BC 2, that means 2 to the power 2 is equal to 4. Similarly, AC closure will be your uh, ABC 3, that means 2 to the power 3 is equal to 8. That means total number of possible, then ABC closure will be your ABC, that means 2 to the power 3 is equal to 8. Total number of functional dependencies possible here is 1 plus 8 plus 2 plus 2 plus 8 plus 4 plus 8 plus 8. This many number of functional dependencies are possible in this case. Similarly, this is your functional dependency, and similarly you can find out all the functional dependency in this case also. Okay, then another thing is that another important thing is here computing if two sets of functional dependencies F and G are equivalent, whether two functional dependency set are there, F and G, whether they are equivalent or not. How to find out that? When F closure is equal to G closure, then the functional dependency set of F and G are equivalent. If F closure is equal to G closure, you have to find out F closure first, then you have to find out G closure. If those are equal, okay, then that is known as equivalent. But in other way, you can say, suppose W2X is present, here W2X is present, here X2Y is present, here X2Y is present, here W2XY is present, and here W2Y is present. If from this functional dependency set you can infer, these are the direct preservation. Okay, from this if you can infer this one, then you can say that both are equivalent. Okay, then redundancy of FDs. Given a set of functional dependency a functional dependency A determining B of F is said to be redundant with respect to the FDs of F if and only if A determining B can be derived from the functional dependency FDs F A determining B, F minus A determining B. Okay, we'll see that. Eliminating redundant functional dependencies allows us to minimize the set of functional dependency. Okay, example, A determining C is redundant in this case, just C. A determining B is there, B determining C is there, A determining C is there. We can infer A determining C from these two functional dependency because here transitive rule is there. Okay, if A determining B is there, B determining C is there, you can write A determining C. Then no need to write A determining C. This is your A determining C is your redundant one. Okay, then redundant attribute on RHS. In a functional dependency, some attributes in the RHS may be redundant. Okay, for example, suppose one functional dependency set is given A determining B, B determining C, then A determining CD. Can be simplified to, in this case, here C can be replaced C can be replaced by B because C is present here. Okay, then B can be replaced by A in this case. Then A can be replaced by we can say this can be A determining B, B determining C, A determining CD can be simplified to A determining B, B determining C, and A determining D. Okay, A determining D, because A determining AD we got, we can write A determining A and A determining D. Okay, no need to write this, then we can write A determining D in this case. Okay, then redundant attribute of LHS. In a functional dependency, some attributes in the LHS may be redundant that can be removed. Suppose A determining B, B determining C, and AC determining D is there, can be simplified to A determining B, B determining C, A determining D. How it is? Suppose here AC is present, you have to check whether any attribute is present at right hand side, C or B. Yes, C is present, that means C can be replaced by your B. Then B can be replaced by A using pseudo transitive rule. Then we can say A determining D. This is nothing but A determining D. That means A determining B will be there, B determining C will be there. AC determining D can be replaced as A determining D. Okay, this is your redundant FTH. Then your canonical cover or minimal cover. How to find out the canonical cover? What is canonical cover or minimal cover? For a given set F of FDs, a canonical cover denoted by FC is the set of FDs where the following conditions are satisfied. F and FC are equivalent and every FD of FC is simple. That is, the RHS of every functional dependency of FC has only one attribute, and no FD in FC is redundant, and the determinant of LHS of every FD in FC is irreducible. Then we can say that this is the canonical cover. Okay. Now we'll take one example. Suppose R ABC, this is a relation with three attributes ABC, and the functional dependency set is your A determining BC, B determining C, A determining B, AB determining C. Then what will be the canonical cover of this functional dependency set? First, make all the functional dependency to which contain right hand side single attribute. Then what will be the functional dependency set? A determining base BC can be written as A determining B, then A determining C, then B determining C is there, A determining B is there, then AB determining C, AB determining C. In this case, just see A determining C, A determining B is two times. Then no need to write it two times. Only one time we can write. Okay. Then in this case, whether any attribute is present at right hand side, yes, B is present at right hand side. That means B can be replaced by A. That means we can write A determining C. This is nothing but A determining C. We can write. Okay, now here we got A determining C two times, here one time, here one time. No need to write it two times, only one time we can write. Then what are the possible functional dependency here? B determining C is there, A determining B is there, then A determining C is there. If A determining B is there and B determining C is there, then it can be using transitive rule. We can derive this, then no need to write this. That means these are the functional dependency which are minimal one. This is the canonical cover. That means if this functional dependency set is given, the canonical cover will contain A determining B and B determining C. Understood? In this way, you can find out the canonical cover. Okay. Then another thing is your membership test. How to check membership test? Suppose one relation R ABCDE is given and this is the functional dependency set. Does AC determining B and D determining AC belongs to F closure or not? How to find out that? Okay, that we have to see. How to find out AC determining B and D determining AC belongs to F closure. For that purpose, First, find out AC closure, and if it contains, if the right hand side will contain D using this functional dependency set, then you can say that this belongs to F closure. Okay, then we have to find out AC closure. Using this, AC closure means it derives AC. Okay, then from AC D can be derived. Okay, D. Then from D C can be derived. C is already present. From C E can be derived. Okay, E can be derived. Then A, from A B can be derived. B can be derived. Okay, then from B C can be derived. C is present, that means A B C D E, all the attributes are derived. Okay, that means AC closure contains B, the right hand side part is present here. That means the right hand side part here is a subset of AC closure. That means we can say this belongs to your F closure. Okay, that means AC determining B is a member of F closure. Okay, then again check D determining AC. Then again find out D closure. Using this functional dependency, D closure will be D, C, C to E can be derived and A can be derived. Then A can be derived means B can be derived. A, B, C, D, all the attributes are derived. Then AC is present here or not? Yes, AC is present here. That means we can say D determining AC belongs to F closure. In this case, this also belongs to F closure. Okay, in this way you can find out. In this case, suppose one relation R, A, B, C, D, E, F is present and functional dependency set is given. Then does AF functional determining BD is a member of F closure? How to find out that? First, find out AF closure. AF closure will be AF. Then F means F can derive AB, B. Then from AB we can derive CE, CE. Okay. Then from EAC can be derived. Okay, AC is already present. A to C is present. C to DF. Okay, D can be derived. That means A, B, C, D, E, F. All can be derived from AF. That means BD is present here. Okay, BD is present. That means AF functionally determining BD can be AF functionally determining BD is a member of or belongs to F closure. In this case, we can say. Similarly, we have to check B functionally determining AC. Okay, then we have to find out BE closure. B closure will be BE first, then BE to AC, then AC, then from AC is present, from AB C is present, or yes, C is present, from C DF is present, DF is present. That means all the attributes can be derived from B. That means AC is present here. Okay, that means BE functionally determining AC belongs to F closure. You can say like that. Okay, in this way we can find out the membership test. Okay, this is all about completion of this database design chapter. Next we will see next chapter is a normalization. Okay.